All right, good afternoon, everyone. Um, my name is Troi Williams, and I am a postdoc in Pratap Tokekar's lab, in the Ross lab. And today I'll be talking about learning state-dependent sensor measurement models to improve robot localization. And so the motivation for my research is, generally speaking, based on the fact that robots rely on their sensors to perceive their environment. The thing is that sensor measurements are biased and noisy, and this bias and noise can vary with the states of the robot and its environment. And so if we poorly estimate these biases and noise, it can reduce performance on robot tasks such as localization, mapping, and so forth, and ultimately reduce safe operations as well. And so, for example, we can consider the images to the right where we have a robot that is navigating throughout a building, and it's using markers on the floor to localize itself within the building using a camera. And so in a well-lit environment, this robot can accurately, or to some extent accurately, localize using those markers. However, in not so ideal conditions, such as a dark room, the localization accuracy can be reduced because of the uncertainty coming from the darkness of the room. And so the goal of my research ultimately is to be able to predict this measurement bias and noise so that we can improve localization and other robotic tasks. And so to do this, during my PhD, we came up with a method called the state-dependent sensor measurement model. And basically it's a model that, given a set of features that we know affect the measurement bias and noise of our sensor, we can predict what the measurement bias and uncertainty will be. And so the idea is that we want to combine traditional sensor models with deep learning methods in order to essentially estimate these measurement biases and noises. And so, for example, if we were to look at the same images from the previous slide, in the well-lit room, we'll have more accurate distributions for the well-lit room situation, whereas in the darker room, we may have more uncertainty. And so these slides just show that the method not only learns the bias and noise pretty well, but also it improves localization for classical methods. And so this one was for a LiDAR pole detection algorithm. And so for the current work that we're exploring during my postdoc, the main question is, how can we exploit these models such that we improve performance on navigational tasks? And so this is motivated by the example where we have an autonomous car or any autonomous vehicle, generally speaking, that has to navigate some environment. So it has to follow some path, and this path has a set of obstacles in it. The issue is that this autonomous vehicle doesn't have any external sensors, so it cannot determine where it is in the world using cameras or LiDAR or anything like that due to some reason. It could be for damage, failure of the sensors, and so forth. And so we have to rely on an external observer in order to observe the pose of this autonomous vehicle in order for it to localize. The issue is that this external observer, which is a drone, uses a sensor that suffers from state-dependent bias and noise. And so, for example, if the drone was to go in any of these states, which are identified by these question marks, we can see different distributions for the measurement bias and noise. And so now the question becomes, which state should we put the drone in such that it observes the minimal amount of bias and noise and ultimately improve our navigational tasks? Now, we could just solve this problem offline, right? The model is fixed once we train it, and then we can just exhaustively search over the input space of the model to find this minimum point. However, in practical operations, we don't actually have access to that optimal state. So for example, when the drone is flying through an environment, we can have obstacles at any given time that prevents the drone from going to that optimal state. So instead of finding this solution offline, we need to dynamically find this during the operation of the vehicle. And so the goal is essentially, we want to find this optimal pose given some objective function based off of some metric that we have for our navigational task. And so generally speaking, the problem is given environment with obstacles and our target, which would be the autonomous vehicle, a target path, and also our measurement model, how do we find this optimal pose that reduces the predictive navigational uncertainty of the target? And so some preliminary results that we have from numerical experiments show that our proposed method, which we're calling DIFOS, matches up pretty well with the brute force approximate ground truth that we're using. And so for both graphs, the axes just show, for example, the distance from the optimal solution or the loss. And for either graph, the lower the value, the better. And so we see that the DIFOS over the course of 1,000 randomly generated worlds, DIFOS is roughly as accurate as the brute force ground truth that we're using. And so these are just a sample of those two samples of those 1,000 worlds where I guess it'll be kind of hard to see far away, but the brown triangle represents the ground truth or the approximate ground truth that we're using. And we can see that it overlaps pretty well with our proposed method, meaning that our proposed method is pretty accurate in finding the optimal solution. And that's it. Do you have any questions?